Thank you so much. Can you hear me well?
Yes. Yes.
I can hear a bit of echo, unfortunately, which is a bit perturbing, but it's my privilege to join you folks. I see lots of old friends online, and it was very inspirational, really, to listen to the project winners and cast my mind back all those years. And they were all so modest and yet inspirational and energetic. So it's really wonderful. Yeah, so this little light-hearted presentation is really based on a paper that we published with a number of valued colleagues. And so you can follow up the essence of the presentation if you like. It's a long-winded title, so I won't linger on this, especially because my time is rather limited. But know that you all know this beautifully classic building, which, you know, my heart raises higher when I caught sight of this building. And I spotted quite a few people online with whom we actually studied jointly here. So it's really fantastic. And research is a journey. It took me first to Germany and then back to the Telecoms Research Institute in Budapest. And then it took me to the United Kingdom. And so currently I'm sitting down here. You see this island where my cursor is circling, which is called the Isle of Wight. And the only reason I mentioned this is just an hour from London on the train. But this is the place where Marconi, for the first time ever, demonstrated the feasibility of radio transmissions across the Atlantic. So that's the Marconian legacy in Southampton. And I landed in this building. We are at the top floor, and so really enjoyed 35 years of exhilarating research at Southampton. It's almost like all the time, you remember those old times when we were getting ready for the exams, and I've been working like that for all the time. So a little bit of an overview, and I know that I'm galloping in places, but research, as I mentioned, is a journey, and it's nice to look back first in the past and then talk about the present times and a little bit about the future. So that's the classic outline, and I won't bore you with a big block of text. You know, often a picture says more than 1,000 words, but I will commence with a historic kind of overview of both radar sensing and wireless communications, and then hypothesize a little bit about what 6G might be. Currently, of course, nobody really knows what 6G will be, and then talk about the conflicting design trade-offs and you know what's in the way of a fully fledged what is called a Pareto optimal radar communication system. So this is the roadmap of our journey this afternoon. And I don't go back to the first generation, don't go back to Marconi all the way, just really looking back to the third and fourth generation mobile systems. And in a way, the enabling technologies have been developed over a decade, and then basically culminated in a standard, the 4G standard, then a decade later, the 5G standard. And now research is well underway for the sixth generation systems. And so you see here this tangential avenue, I called it next generation parkway. A parkway is a broad street, right? A broad road. And currently it's overly broad, but the research is really evolving very swiftly. And some of you who know me well, I spotted this afternoon the quantum session, and I'm quite interested in next generation technology all the time. But today I'm not talking about quantum communications, rather focus on what 6G might be. So that was the sort of wireless history in a nutshell in almost like 60 seconds. And this is now the hitchhiker's guide to radar and joint radar and communications. And it's interesting that the first paper really dates back to 1963, but then there was a long gestation period. Not much happened really. And Thomas Zwick would know that Werner Wiesbeck, he was a visionary scientist in Germany, and he wrote a wonderful paper about the capabilities of OFDM in terms of supporting both communications as well as sensing functions. But as I said, there was a long gestation period, and it wasn't until sort of 1994 when the first patents on MIMO communication systems were granted with a view to support radar sensing as well as communications. And then, of course, the developments kind of sped up a little bit. And a very substantial development was when Thomas Marzetta, then he was working for Lucent in New Jersey, came up with the idea of what he termed as massive MIMO schemes or large-scale MIMO schemes with lots of antennas. And this I will revisit as we go along in a bit more detail. So that really sort of sums up the history. And right now, the momentum is just unbelievable in joint sensing and communications. There is an emerging technical committee under the IEEE Communication Society. And so let me just really sort of make a statement here. Today, my thesis here is that the single objective, single function optimization is really over. And we as a community have to start researching Pareto optimization. So Pareto optimization is really a very challenging field of optimization theory, where the multi-component objective function really has lots of parameters, and I will come back to this in much more detail as we progress through the talk. But effectively, it contains, the optimum Pareto front contains all the optimum solutions, and it's not possible to improve any of the parameters or metrics without actually degrading some of the others. And a blatant manifestation of this is, for example, where we can't improve the throughput without increasing the power, for example. That's basic Shannonian theory. There's many other famous trade-offs, but I won't be talking today about the trade-offs. I actually want to really delve into the Pareto principles in a bit more detail. So what's the manifestation of this in practical terms? And many of you know this spider diagram. Casting my mind back to IMT 2000, which was about 20 years ago, really the European Telecommunication Standardization Institute set out to lay down the foundations, the set of criteria the next generation systems had to comply with or satisfy. So you can see here that these dotted lines actually indicate the associated trade-offs. And again, I won't be sort of really delving into too much detail, but suffice to say that, again, the throughput versus the power consumption becomes blatantly obvious. But I can also improve, for example, the bit error ratio if I reduce the throughput or increase the power, or increase the delay of an error correction coding scheme, or increase the complexity by iterating more in a turbo decoder. So there's many aspects of this. And all I wanted to sort of highlight in this context is that over the years, over the past 2 decades, these spider diagrams have sort of expanded a little bit. As you can see, we've got here the next generation networks, namely 6G currently. And obviously, this is just a hypothesis how the various trade-offs will pan out, but there will always be a trade-off. And we know this also very well from our personal lives. Somebody might like to really dedicate their lives to science. Others, like Donald Trump, might dedicate their lives to making money or becoming famous through politics. And, that's single component optimization. But most people would like to have just a normal life and aim for a reasonable balance. So I hope you got the gist of what I'm trying to say with the Pareto optimum design in this context. So the question arises really, is RADCOM or SenseCom only on about spectrum sharing, or is it only on about hardware sharing? I mean, there is obvious sort of synergies between the two areas, but both communications and sensing have been developed pretty much in isolation, and sometimes, in fact, in a bit of competition with each other. And so I raised this research question up front in the title: is this going to be the 6G killer application? And obviously, at this stage, nobody really knows what will be the killer application, but the customer will only pay for things that they benefit from. And so there are, sort of rather plausible benefits in using, for example, sensing in terms of localization. For example, we heard about this wonderful final year project or about the time of arrival investigations. And that's one way of locating objects and people, but that is really the essence also behind radar style sensing. But there's much more we can do in this context, and you can see in the illustration at the bottom where gestures, for example, can be recognized by using appropriate analysis. And so the next illustration, and again, I'm glossing over a mountain of things in this context, but gesture cycles can be easily recognized even in terms of the received signal power, the RSSI of 5G handsets or 4G, even 4G handsets. But of course, we can have much more kind of savvy, much more detailed analysis in this context. And in the COVID era, we obviously enjoy the benefit of having a credit card, which doesn't require physical context or touch rather. But obviously, there are other sort of gesture-controlled operations that we could think of. And I'm more of an engineer, so I will be, focusing a little more on the enabling technologies rather than these applications. But it's very plausible, and it would be more like an after-dinner speech or maybe during the banquet of the conference where we could talk about these applications. We could even have a competition who's got better ideas. But, the autonomous driving, the robotic cars, and so on, these are also very, very tangible applications. You see here the yellow beams, for example, which indicate that we could use it for, for example, for platooning on the motorway. In other words, hand-free driving. And then we could also use these kind of orangey beams in order to detect objects and avoid collision and protect people and pets and so on. And, the list really, really goes on. But I want to delve into a bit more technology because obviously this is a technical conference, right? Even though this is the last session in the conference. So I sort of touched upon, the research questions. Is it on about, spectrum sharing, or is it on about hardware sharing? Because clearly there is competition for the spectrum. There's even competition for the spectrum in the wireless area. And so in the olden days, up to even 3G, we used the sweet propagation properties of the lower frequency band, starting from 450 megahertz, moving up to 1 gigahertz and 2 gigahertz, etc. And this is where we can have larger cells with lower attenuation. But as the frequencies goes up, obviously the path loss goes down, and so we need more transmit power, or we need really, really high gain MIMO systems, multiple input, multiple output systems. And so in this context, 4G and 5G already using spectrum sharing, but there's a more to sort of this story. I now move on just to touch upon the hardware sharing aspects for a moment. And so we could obviously work on joint waveform design, but the challenge is that whatever is efficient for communications is not particularly efficient for radar or sensing type applications. And so today I won't be really talking about waveform design because my time is so limited. Won't be talking about synchronization, but I will talk a little more in detail about the MIMO systems which are now becoming ubiquitous as you drive along the motorway or any mobile tower. You see the plethora of antennas, and also we heard again already in the final year projects about artificial intelligence and machine learning, and these are extremely good tools, especially for upper layer optimization in the face of uncertainty, when we don't know the position, we don't know whether there's enough power, and so on. So this illustration down here just shows a downlink scenario where we have a dual function radar and communication system. DFRC is another acronym for RADCOM. And so we've got the radio frequency chains, but of course, these are the most power-hungry components of wireless systems. And hence, we want to minimize the number of radio frequency chains. So we usually use what is called hybrid beamforming, where there is a limited number, a modest number of RF chains for digital beamforming. And then there's just phase shifters, which actually don't pick much power. And so you see here again the differently colored beams used for localizing objects as well as used for communications. And I will delve a little more into the number of transmit and receive antennas now. But before I do that, just a few thoughts on really hypothesizing what 6G might be. And I will talk about four pillars of the sort of current thinking in the community. The first one being the sort of integrated space and ground integrated networks, where literally everything, including planes and satellites and ships and drones and terrestrial base stations, constitute an amalgamated system. Of course, there are huge challenges, but that's a research ambition. And there are already very, very good solutions using low Earth orbit satellites and so on. The second one being basically the frequency ranges that we harness for different purposes. And the sub-6 gigahertz is really not so good for enhanced mobile broadband type communications. So the millimeter wave band is being considered, although it has been set aside for future investigation in 3GPP, the standardization body. And then, of course, terahertz for very, very short distances. And again, the ubiquitous AI, artificial intelligence for processing big data. And finally, of course, security. Again, I allude to the quantum session we had previously in the conference, and the physical layer security. These are all aspects that require further research and might find their way into 6G. Now, a couple of, and I promise there's only these two very, very simple equations. I know it's late in the day. So just to mention, the classic Shannonian law, of course, says if I pump in more transmit power, unfortunately, this logarithmic function limits the benefits in terms of throughput, in terms of capacity, whereas the bandwidth B is really a linear function, or the capacity is a linear function of B. And the spectacular success of MIMO systems is really based on the fact that the MIMO capacity, as opposed to the single input, single output capacity, is a linear function of the number of transmit and receive antennas, whichever is smaller. So there are many, potentially an infinite number of MIMO types, but in this context, just wanted to mention that the beamforming is the most promising one for the joint radar sensing and communications applications. So a few words about this, rather than glossing over all the blast type schemes, etc. So the trouble is that we already stated bandwidth is great because the capacity is linearly proportionate to the bandwidth. But as we increase, if we look for more bandwidth, we can only find it at higher frequencies. And as you can see, the path loss is increasing, very dramatically with the frequency. So the terahertz band really has a very, very high attenuation. So what can we do? Well, we can use, tons and tons of antennas. And nowadays, people are talking about literally hundreds of antennas, because if we operate, for example, at 60 gigahertz, the wavelength is only 0.5 centimeters. And so we can actually allocate real hundreds of antennas on a panel with 0.5 centimeter spacing. Again, I'm glossing over the practicalities here, but this is an illustration which actually shows how many antenna elements we would need in order to compensate for the extra attenuation as we increase the frequencies. And so you see here down the frequency. At low frequencies, we don't need so many antennas, but as the frequencies increase, especially at 60 gigahertz, when we've got the oxygen absorption zone, for example, there's really a big hike or spike rather in the number of antennas. So we started out from wanting, more bandwidth, but more bandwidth is only possible at higher frequencies. Then we need many antennas to get very sharp pencil beams in order to achieve this. But then we need very powerful AI-assisted beam search algorithms in order to find them. So drawing closer to conclusion, really, just to sort of highlight two specific aspects in this context, because I sort of focused on the MIMO systems. And you see here again the two different colored beams, and the blue beams indicate here the radar-oriented antennas in a sort of shared application, and the mauve-colored or maroon-colored antennas indicate the ones for communications. The other design option is that actually use all antennas for both purposes. And we will see the benefit here because you can see that the most important metric in this context is really the peak to side lobe ratio of the beamformer. And if in the investigated context you find the associated data in this paper, we only get about 7 dBs peak to side lobe ratio if we have the separated deployment, because we've got less antennas for both radar and communications. Whereas if we have a properly shared deployment, then we get 8 dBs more. So actually you need almost 10 times less power. And that is a very substantial factor. Again, I'm not pretending that this is the only factor in this context, but glossing over lots of things and really highlighting some important points for, food for thought, really. So future research, what is the future holds for 6G and for joint sensing and communications. In this context, I'd like to highlight in the spirit of this previous illustration here, that there are, again, a huge variety of MIMO schemes, but the three basic types are the multiplexing, the space-time coding type diversity gain MIMOs, and the beamformers. And so it is possible to combine all these functions if we have large enough antenna arrays, as I have highlighted in this slide. So that needs further research, although we've got some tangible results in this paper and in our related book. But I wanted to really just close on a very, very important point, namely that we shouldn't really optimize the systems for bandwidth efficiency because they become very complex, for example. And the throughput becomes low because we can't use high throughput modulation schemes. We shouldn't optimize them for bit error ratio. We should really make the system near instantaneously adaptive so that we can load up whatever operating mode is necessary. And this is, of course, centered on the good old-fashioned concept of software-defined radio. But in the joint sensing and communications context, there are even more grave challenges which we as a community have to solve. And so I return to my original thesis, really, that the single objective, single function optimization era is over. We have to design mobile transceivers like the Swiss Army knife, which is not quite as good as a pair of pliers when you buy it for that one and only purpose, but it has all the optimum points, all the optimal operating points of a system which we can upload on a near instantaneous basis. And I'm really done, and thank you so much for your patience with me. I haven't even touched upon a whole plethora of amazingly interesting and challenging technical problems. And so research is ongoing. And my hope is that at some stage, I will rejoin my old friends I've seen in the ODS, like Pakshigeza, with whom we actually had a joint paper, and Tibor Sinclair, and so on. So thank you so much.